All right, guys. Happy Friday. How you guys doing? You guys are doing all right. So we are up to day 2 of our probability. All right. So yesterday we talked about some basic probability. All right. Hopefully everything in there made sense. Right? If not, send me a question. But today we are going to be talking about two-way tables and conditional probability. All right. So I usually give you this as a warm-up. So try to do up to the Venn diagram part at least, because I want to make sure you have the right numbers before you actually start what's below. But go ahead, fill out that table, and try to change what you see there in that table into a Venn diagram. I know it's kind of a little weird of an ask, but try your best. All right. So filling in this table should be no problem, right? 108. That should be 232. This is going to be 116. 108 plus 54, 162, and that's going to be 62. All right, so fill in table, easy peasy. All right, at least I hope so. But let's change this to a Venn diagram. If you haven't already, really try to make it into a Venn diagram. All right, pause the video. It's a good exercise. It's a good thing to practice. But here we go. So I notice I have two main groups, right? Android and iPhone. So I'm going to make my Venn diagram have those two circles. Man, it's so much nicer this year when you can draw perfect circles. So there we go. So one of these circles I'm going to call iPhone. So here's my iPhone circle. Here is my Android circle. So how many people have an iPhone? And I see that number is 232. So you might be tempted to put 232 in the circle, but what about this overlapping part, right? Are we going to have some overlap between iPhone and Android users? So instead of putting the 232 there, I'm going to put the 232 outside. Let me see where I want to put it. I'll put it over here. I'm going to put this 232 just outside the circle. You don't have to, but I like to do that because that tells me whatever numbers I have in this iPhone circle, right, should add up to 232. So all the numbers in here, that's going to be 232. So instead of just trying to fill in this piece first, well, I definitely know the intersection of iPhone and Android users because I see I got 124 use both. So that number I know for sure goes in that middle section. Well, now if I know it's 124 here and the entire circle needs to add up to 232, well, I can do 232 minus 124, and I can get iPhone only users are 108 individuals. Right, so for Android, and also, of course, that number is just right over there, by the way. So if you have an iPhone and no Android, right, in this scenario, you're going to be an iPhone exclusive user. So, all right, so that was pretty simple. So same thing here. You can just put a 62 here. And if you want 62 plus 124, right, that's going to give us our Android total. And so we can put a little 186 over here if you want. And there we go. You probably think, all right, there's my Venn diagram. But aren't we missing information? Can we tell in this Venn diagram how many people have no iPhone and no Android? No, we cannot. So what you need in every single Venn diagram is a rectangle. And this rectangle represents every single person surveyed in whatever we're looking at. So in this case, in this box should be a total of 348 people, right? So if all this is to add to 348, well, how many people don't have iPhone or Android, they're going to be outside those two circles. The 54 is going to go just anywhere. You can put it anywhere floating around here. Right? I'm just going to put it in the top right. So like this 232 and this 186, right? This 348 represents the total amount inside the rectangle. Right? And by the way, these numbers here are optional. You don't need them technically as part of your Venn diagram, but I like to put them in just for easy reference. All right, and it's going to help later on once we do harder problems. This one was very simple, but later on it might help to have those numbers there. And so if we add up 108 plus 124, what is that? 232 plus 62, that's 294. 294 plus 54 is 348, right? So all the numbers inside add up to 54, right? Don't look at those numbers. All right. So let's take a look. If a student is randomly selected from the sample, so when I say from the sample, kind of like sample space, like everyone or all the outcomes, our sample is out of everyone. So we sampled or we surveyed 348 freshmen. So that's going to be our total. So we're saying out of the 348, what's the probability that a student has an iPhone? So how many people had iPhones? 232. We can look at the table over there, or we can look at this Venn diagram, look at that 232. But 232 people out of 348 had an iPhone. And if you simplify, I think this is actually equal to 2/3, but again, you don't need to do that. What's the chance that someone has both an iPhone and an Android? We're going to be looking at that overlap. 124 out of the 348 had an iPhone and an Android. So that means if you randomly pick someone, right, assuming you have an equal chance of picking anyone, you would have this probability that that person has both an iPhone and an Android. Right, so has an iPhone but does not have an Android, that's 108 people. So 108 out of 348. Has an iPhone given he or she has an Android device. Right, so first three questions were really basic, right? This one, we have this word given. So we call this a conditional probability. Right, when you see this word given, that's going to indicate a conditional probability. And we'll take notes on this in a little bit. But the condition is that this person has an iPhone. No, sorry, that is not the condition. We're trying to find the probability of a student has an iPhone given he or she has an Android device. So I'm sorry, the condition that the person has to fulfill is that they have to have an Android device. So we're only looking at people with Android devices. So we're not looking at this full sample of 348 students. We're looking out of this sample of 186, right? Out of these people with Androids. So out of this 186, how many of them have iPhones? So out of that 186, 124 of them also have iPhones, right? That was the overlap. So there's a pretty good chance that given someone has an Android device, they also have an iPhone, which doesn't make sense to me, but just go with it in this case. And what is the probability that someone has an iPhone or an Android device? So iPhone or an Android, you might be thinking we can just add up these two numbers, right? But that's going to be more than 348. And that's because we're double counting this 124 if we just add up those two numbers. So using the Venn diagram, what you would do is you would do 108 plus 62 plus 124, right? Because 108 gives you this part, 124 gives you that part, and 62 gives you that part, right? So altogether, that's the entire set of iPhone or Android users. So two ways to do it. You can add up those three numbers, 108 plus 124 plus 62. what is that? 170 plus 124. 170 plus 1. Right, that's going to give us 294. That's one way to do it. We can also do the total number, right, minus people that don't have an iPhone and also don't have an Android. So we can minus the neither category because that's out here. So we minus that, that's going to give us everyone in there. So that's another way we can do it. We can also do 348 minus 58. That's also going to equal 294. I think I subtracted the wrong number. That has to be 54 for it to work out. Is that right? Yeah, the neither is 54. Or we can also do one more way. Looking at the table, right? It's actually easier in the Venn diagram to calculate this. But looking at the table, we could do how many people have Android and iPhones. So 186 people have Androids, 232 people have iPhones. But we need to subtract the overlap, right? 124 people have both, so we need to subtract that 124. So third way we can do this is 186 plus 232 minus the overlap, 124, and that should also give us 294. So anyway, the probability someone has an iPhone or an Android device is 294 over 398. All right? So a whole bunch of ways, but this is actually going to be the way our formula tells us how to do it. So we're going to come up with a formula in a little bit, but this is the way we're probably going to be doing these problems, or at least I will be doing it most often. But again, there's lots of ways to count the number of people with an iPhone or an Android using either the Venn diagram or the table. Right? A little easier using the Venn diagram. It's more visual. You just want to sum up those numbers in there. All right. So I want to take a look at the card depot station from the last lesson because we can get some good definitions from here. So if I ask, what is the probability of drawing a red card or a 7? So how many red cards do I have? I'm going to have 26. All right, so I'm just going to write down the probability of drawing a red card. That's 26 out of 52. What's the probability of drawing a 7? So we have 4 7s in the deck of cards. That's 4 out of 52 of drawing a 7. So if you remember from yesterday, we said we could add two probabilities together, right, if they had no overlap in their events occurring. But as you can see, drawing a red card and drawing a 7, right, has overlap. They overlap over here. So isn't that overlap the chance of drawing both a 7 and a red card? In other words, drawing a red 7 card, or a red 7, right? And that happens 2 out of 52 of the time. So we actually need to subtract that overlap. And that's pretty much what we're doing here. When we did 232 plus 186, right, we had to subtract this overlap of 124 to avoid double counting this, right? To avoid double counting the iPhone and Android users. So, I don't know what I'm doing now. So, same thing here. We find the probability of drawing a red card, add it to the probability of drawing a 7, and then we have to subtract the overlap or the chance that both occur at the same time because we don't want to double count. So when we do this, we get a 28 out of 52 chance. Right, so I know it's probably easier just saying, okay, that's 26, and then we got 2 more 7s that we can draw. 26 plus 2 is 28, right? But this will give us a formula that always works. If you add up the individual probabilities of drawing a red card and a 7, and you subtract the probability of the overlap, or the probability of both events occurring at the same time. right? And let's take a look at some conditional probability problems over here. What's the probability of drawing a red card given that a 7 has been drawn? So again, anytime you see the word given, that's conditional probability. So we're not looking at the set of all cards anymore. A 7 has already been drawn. So which cards are we looking at? We're looking at these cards. A 7 has been drawn, right? That is a given. So that's our condition. Under the condition that we already got a 7, what's the chance now of drawing a red card? Well, if we got a 7, 2 of those 7s are going to be red. So 2 out of the 4 total. So if you drew a 7, there's a 50% chance of it being red, right? So that's 2 out of 4. Hopefully that makes sense. If we switch the condition around, what's the probability of drawing a 7 given that a red card has been drawn? So our condition now is that we already got a red card. Well, we got a red card. That means we could have gotten any one of these 26 red cards, right? How many of those 26 red cards are 7? Well, just 2 of them. So 2 out of 26. So order, of course, definitely matters for a conditional probability, right? Depending on what your condition is, that's going to be a big difference. So the order matters. So the probability of drawing a red card given that you have a 7 is 50%. The probability of drawing a 7 given that you got a red card is only 2 out of 26, right? So let's just talk about some things that we can define now. Let me copy and paste from here. So yesterday, I just want to put down all the definitions. So I want to put down this guy also. Copy, paste this here. So probability of some event occurring, A, is equal to number of possibilities that meet my conditions. You know, I actually like the word outcomes better, but either word is fine. Over the number of equally likely outcomes. All right, so that's the probability of something happening. I want to just talk about some notation. The probability of something and something else happening, we're going to notate like this. All right, this means the probability of A and B happening. Probability of event A and B occurring. Right, at the same time. So if I go back to here, I could have asked the question like, what's the probability of getting a, I don't know, a face card and hearts. Make that heart red. Those hearts are red. All right. So what's the probability of getting a face card and a heart? Well, we look at all the face cards. We look at all the hearts. Well, I can highlight all the hearts, right? And we see there are 3 cards that meet both criteria, right? So the probability of a face and a heart is 3 out of, well, all of the cards. That's 3 out of 52, right? There is no condition here. I'm going to say given I got a face card or given that it was a heart, right? That's just what's the probability of drawing a face card that has hearts on it, right? Or probability of drawing a face card and that is also of hearts, if that makes sense. So that's 3 out of 52. All right, so that's an and probability. The way we notate or is we're going to use the U shape. So when I said what's the probability of drawing a red card or a 7, the way we would write this is probability of red and then U, right? U for union, that's or 7, right? So the probability of A or B, that's the or symbol. And in words, this is the probability of A or B, event A or B occurring. All right, so this guy here actually has a formula that we were talking about earlier. So the probability of drawing a red card or a 7, well, let's figure out what we did. We said this was equal to the probability of getting a red card. It's probability of red, plus the probability of getting a 7. And what did this 2 out of 52 represent? Well, that was the overlap, or the probability of getting a red 7, or red and a 7. So probability of red and 7. And that's going to be our formula. We're just going to replace red with A and 7 with B, right, for in general events. So the probability of A or B is going to equal the probability of A plus the probability of B, right, minus the overlap, probability of A and B. So if you remember yesterday, we said we could sum up two probabilities, right? We could just add probabilities, and we said we could do that when there was no overlap. So if I just take a look at the notes from yesterday real quick. Take a look at the actual notes we did. Right, if two events have no outcomes in common, what that means is the probability of the two events, let's just call them A and B, equals 0. It means there's no chance of two things happening simultaneously. So that's why when we did like the probability of rolling an odd number or 2, we could just add the probability of rolling an odd number with the probability of rolling a 2, because there's no chance of rolling an odd number and a 2, right? That probability is equal to 0. So I actually don't even like the fact that I wrote this piece here in the notes, right? But it is true. But in general, you can just always use this formula, all right? And that was just talking about a special condition, right? If events A and B cannot happen simultaneously, and a lot of times that's going to be true, right? But not always, so you have to be careful. But events A and B cannot happen simultaneously, then, well, then that's impossible. Then probability of A and B is going to equal 0. So that was what was in the notes on the first day, all right? So far we've gotten probability, in general definition, we did and or, and now I want to do conditional probability. So conditional probability. The way we notate something given something else is what's the probability of this event A occurring given that B has already occurred. So that little line that represents given. And the way we would read this is probability of A given B. Right, so nothing too crazy. So again, it's saying under the condition that B has already happened, right? That's a given. Now, what is the chance of A happening after this has already happened, all right? So yeah, I'm not even going to write those out again. Okay, let's keep going. So whole lot of writing here. I really took out a whole bunch of questions because you actually had to fill this in before, but I just filled this in for you because it's kind of silly. But anyway, evaluate the following and write a sentence to explain the meaning of each. So let's read the question. The school board of Waldo in a rural town in the Midwest is considering building a new high school primarily funded by local taxes. They decided to interview eligible voters to determine if the school board should build a new high school facility to replace the current high school building. There is only one high school in the town. Every registered voter in Waldo was interviewed. The data from these interviews are summarized below. All right, so evaluate the following and write a sentence to explain the meaning of each. So what's the probabilities that someone voted yes, given that they are in the 41 to 65 age group? So I'm going to write that down. What is the probability someone voted yes, given that they were 41 to 65 years old? So based on that given, we are not looking at all 515 residents or voters, right? We are looking at these guys, right? Because that was our condition, given that they're 41 to 65. So how many people are 41 to 65 years old? 149 of them. And out of those 149, how many people voted yes? Looks like 30 plus 36. So 66 out of 149 people in that age group voted yes. So the chance that someone who was 41 to 65 years old voted yes is 66 out of 149. All right. Compare that to what's the chance that someone who voted yes is this certain age. So a lot of people get these two things confused. I know it's like kind of weird. It feels like maybe these should be the same thing, right? But if you take a look at our card example, I think it's a lot easier to see why it's obviously not going to be the same, right? But when you get into like real statistics, like dealing with real life stuff, right, it gets confusing, right? But this is what is the probability that someone who voted yes is going to be 41 to 65 years old, right? Or what's the probability of picking someone who's going to be in that age group given that they voted yes? So same question here, just switch around the given and the probability you're trying to find with the condition. And so this will be, given that they voted yes, how many people voted yes? That plus that, I think that's 273. And given that they voted yes, how many people were in that age group? 66 of them were in that age group, so 66 out of 273. All right, so again, as you can see, very different numbers. And I'm just debating whether I want to write it out or not. I'm just going to copy and paste. So this answers the question, what is the probability that someone aged, or someone is aged 41 to 65, given that they voted yes? All right, so there's a 66 out of 273 chance that someone aged 41 to 65, that someone is that age, given that they voted yes. All right. So one more example down here. Obedience School for Dogs is a small franchise that offers obedience classes for dogs. Some people think that larger dogs are easier to train and therefore should not be charged as much for classes. To investigate this claim, dogs enrolled in the classes were classified as large if they were 30 pounds or more, or as small if they were under 30 pounds. The dogs were also classified by whether or not they passed the obedience class offered by the franchise. 45% of the dogs in the class were large, 60% of the dogs passed the class. Records indicate that 40% of the dogs in the classes were small and passed the course. So we could definitely fill in this table down here with percentages, right? But a lot of times, well, it doesn't really matter. A lot of times you don't want to use percentages, though. Sometimes you just like some pretend numbers, and that's what we're going to be doing here. We're going to be completing a hypothetical 1,000 two-way table. So in the original scenario, right, we had no idea how many actual dogs were involved. There could have been like 100 dogs that took this class, or there could have been 1,000,000 dogs that took the class. But what we're going to do is we're going to complete a hypothetical 1,000 two-way table, right? And sorry, by the way, what we're doing, these are called two-way tables. So hypothetical 1,000 is we're going to pretend that there were 1,000 total dogs as a sample, or as the sample. So again, we don't know how many dogs there are. If I asked you to make a hypothetical 10,000, 2,000 two-way table, then you would just make the total 10,000. So we're pretending there are 1,000 dogs. All right, so let's fill in this table now. 40% of the dogs in the class were small and passed the course. So that's going to be 400 here, right? Because 40% of 1,000 is 400. And 45% of the dogs involved in the classes were large. So that's going to be 450 here. And 60% of the dogs passed the class. And so this is going to be 600, which makes that 200, which makes this 250, which makes this 550. That makes this 150, and that's 400. And you should always just double check. Does 600 plus 400 equal 1,000? Yes. Does that plus that equal 1,000? Yes. And so estimate the probability that a dog selected at random from those enrolled in the classes passed the course. So from the dogs selected at random, we're going to be out of all the dogs, right? From those enrolled in the classes, passed the course. 60% passed the course, that is 600 out of 1,000. You can write this as just probability of pass equals 600 out of 1,000. A dog was randomly selected from the dogs that completed the class. If the selected dog was a large dog, what is the probability this dog passed the course? All right, so this is a given conditional statement. So I want you to write this with the correct mutation. We're looking for the probability that this dog passed, right? So probability of pass given, so we're going to use that vertical line, given that the selected dog was a large dog, right? So even though it doesn't explicitly say, like, given it was a large dog, it says if the selected dog was a large dog, what's the probability that they passed this course? So under the condition that the selected dog was large, that's our given condition. So probability of pass given that they were large, that's going to equal, there's 450 large dogs and 200 of them passed. Right. Next, a dog was randomly selected from the dogs that completed the class. If the selected dog is small, what's the probability that this dog passed the course? Probability of passing, given that they were small. And that's going to be 400 out of 550, if I remember correctly. Yeah. Cool. And do you think that dog size and whether or not a dog passes the course are related? All right, so let's take a look. What's the chance that a small dog passes the course? And so let's actually calculate this probability. I'm going to get this as a percentage. So 400 divided by 550. That is a 72 approximately 7% chance that if the dog is small, they're going to pass. Whereas for a large dog, 200 over 450, this is about 44.4%. So do you think whether dog size and whether or not a dog passes the course are related? I definitely do. It definitely does look like, given that if a dog is large, they have a much lower probability. Maybe they are harder to train than small dogs. So yes, and if asked why, you can point to this fact that a much smaller percentage, or there's a much lower probability that a large dog is going to pass than a small dog is going to pass. So, yeah, that's that. Pretty, hopefully nothing too crazy today. The main meat of today was conditional probability, and also we defined a formula for finding the probability of A or B. Okay, so that's going to be it, guys. Enjoy the weekend. All right, happy Friday again. And oh, sorry. Last thing, the tests. I actually don't know if I'll be able to finish grading this weekend. I'm actually like very behind on things, so I'll see. But that is my priority. I'm trying to get it done this weekend. And so if I don't finish this weekend, though, please don't be too upset. But I will be trying. All right, guys. Take care. See you guys later. Bye-bye.